Hello. I was thinking of going through Colloquium 2 topic today regarding calculations in genetics, specifically targeting markers in calculations. Now, markers are a little bit tricky to grasp, but I will try my best to explain it as well as I can. I will go through the rules, which doesn't seem plentiful at first, but these are complicated to apply into the calculations. I will also get into all of the calculations on both documents that are up on RSU. So that could mean that this will be a very long video, and I apologize for that. Still, I think this would be quite fruitful for anybody who's trying to get into these types of calculations right now. Now, another important thing is that this is a topic in Colloquium 2. So markers will not be brought up in Colloquium 1, just in case you're a little bit lost, as well as the fact that all of the previous information that we learned in X-linked recessive, in autosomal dominant, as well as in autosomal recessive are still very valid. So we are building up on the information that we previously know. The only thing that we're adding in is the idea of markers. Now, starting off, what exactly are markers? Well, if we say that we have a piece of some genetic information right here, this will represent an unhealthy allele or pathogenic allele. Then we put almost like a flag here, stating that this will be represented by either a number or a letter, but in this case I chose A. Meanwhile here, for this allele, which doesn't represent any pathogenic variants, as we can see here, this we flag also. So we don't only flag pathogenic, we also flag non-pathogenic, and we state that this could be B. Sometimes they use numbers instead of letters, but most often I see letters used. So in this case, we have this unaffected person right here, but they have a marker that marks for a pathogenic allele. Therefore, this person is definitely a carrier. Another important fact to say is that markers are not sick or pathogenic in and of themselves. They are just like small flags that we put on the pathogenic, or not, we're not physically putting anything there, but we are flagging these this genetic information that we're getting, and therefore it's always represented with some sort of symbol, letter, or a number. So if I ever say this is a sick marker, just know that I don't mean the marker is sick, I mean that the marker represents an allele, a pathological allele. So rule number 1, marker stands for flags that marks for pathological or non-pathological alleles, just like we learned up here. So it's very important that for every bit of calculation that we're doing, we always have to mark down some important information. The first one is writing down the common pathological. See here, I already did the mistake, but common marker that marks for a pathological allele. In our case here, let's say we have this person that's from the background. He's affected and he has the marker A. This person right here is also in this pedigree tree, even though we can't really see it here, but this person is also connected, and he has the marker also that marks for an allelic pathogen, which is A, and he's also affected. That's how we can know that the common marker between these two affected is A, and therefore they must mark for the pathogenic allele. So that's why it's always important to mark down in your calculations before you start with anything, what is the common pathogenic allele between these affected individuals in the pedigree tree. Number 2 is a very complicated topic, but we'll try to go through this anyway. Crossing over means that a risk could still be applied to a marker marking for a non-pathological allele and vice versa. There's always a small chance for pathological allele marker to not mark for a pathological allele and vice versa. What does this mean? Well, first of all, let's explain crossing over. Now, what is crossing over? Crossing over is something that occurs during meiosis, during the production of gametes, where one allele gives off information to another allele, almost copying what it has here into the other. It sort of forms a bridge between two chromosomes, which we can kind of see here. So we have two chromosomes here. Now there's a bridge forming in between them, and one of the chromosomes, or a little bit of genetic information, is copied into the other. Also vice versa. It doesn't have to go either one way. It's very random, but there is a small chance that instead of having two different alleles, let's say there's A and A, instead this copies its information into here, so we get this, or this copies its information into here, so we get this instead. However, the markers are not going to change. So if we, for example, had a marker here that's number 1, and then a marker here that marks as number 2, this will still be the same, even though you can see here that the pathological allele has been copied into what would normally be a non-pathological allele. It still has the healthy marker. That's why it's very important to take into account that even though there might be healthy looking markers, this occurrence could still happen where the pathological allele, or vice versa, could copy its information into the non-pathological allele. They would still have the same marker. So in our case here, for example, this is no crossing over occurring. So we have this pathological allele, I would say, or a horrible representation of it. We can see here that this little bit of information is the pathological allele. This would be a part of a chromosome. Here in B, it's a non-pathological allele because it is in red, pretty much. It isn't represented in red, and it goes accordingly. Here we have a crossing over occurring that is pathological, meaning that the pathological part of the chromosome here, this little allele here, will be copying itself in to the non-pathological allele, creating this pathological allele right here. Here, we can also have non-pathological pathological crossing over, where this non-pathological allele here copies its information into the pathological allele, creating two non-pathological allele types. So these all could be occurring, therefore it's very important to note what is the chance for crossing over to occur, and to know for a fact that even though we can see here A is the pathological, or the marker for the pathological allele, even though this person right here hasn't gotten the pathological allele marker, it doesn't mean that he's healthy or non-carrier. There could still be a small chance that this has occurred, where even though we have the healthy pathological marker or non-pathological marker, there could still be a pathological allele within this chromosome. So that's what crossing over is, very, very simplified. Now, how do we value this crossing over? How do we value the risk? And that is where we get Centimorgans, or CM, which stands for the chance for a non-pathogenic allele to become a pathogenic allele, despite the genetic marker, and vice versa, of course. There's often a low chance, usually 2, 5, or 10 centimorgans. And we always have to write down if there's a low or a high chance of carrier/affected probability taking into CM account. We'll get to this soon, but let's start with the example of 2 centimorgans, which would be a 2%. So this is very easy to remember. 5 centimorgans represents a 5% chance, 10 centimorgans represents a 10% chance, and vice versa. So that is very easy to remember. What does this mean? It means that there is a 2% chance of crossing over. I already wrote it down. There's a 2% chance of crossing over occurring. So for example, in this case, which we kind of mentioned earlier, we have this pathological allele marked by A, but here this marker marks for non-pathological alleles, right? So we would assume this person is healthy. However, if crossing over occurs, this could still look like this right here, because the pathological copies into the pathological, or to the non-pathological. Therefore, just because we have a healthy looking marker doesn't mean that this person isn't a carrier or affected. Therefore, we have to write down there's a 2% chance that this person will be either affected or carrier, because he can still carry this pathological allele despite having a healthy looking marker due to crossing over. If non-pathological crossing over occurs, which means that we have let's talk about this first. This is a low chance of affected. Low chance. Because there's a low chance that the crossing over has occurred, right? So we have a low chance of this person being affected or a carrier. Here, we would have a high chance. Why? Because the chance for crossing over to occur is still low. It's always low. However, in our case, this marker, which stands for the non-pathogenic allele, has been given to this person as well, meaning that oftentimes we would assume him to be affected or a carrier. 100%. However, again, this person could still be experiencing this crossing over phenomenon, which means there's still a 2% chance that this isn't the right allele or isn't representing the right allele. In our case, this would happen. So the healthy allele would copy into the unhealthy allele, and therefore, even though we have a marker that looks unhealthy, the allele is perfectly healthy. That is why that we always have to redact the crossing over chance from the 100%. So in our case, 100% minus 2%, which equals to 98%. So now, instead of 100% chance for this person to be an affected or a carrier person, there's now a 98% chance for him to be, because there's a 2% chance that even though we have this marker, we actually have this type of allele. And now we always have to write the high risk of affected and the low risk of affected. And what does that mean? We for high risk, which means that the person is showing the marker that usually marks for pathogenic alleles, which means there's often a high risk for them to be a carrier, minus the risk of non-pathogenic crossing over. So when we come to high risk of affected and low risk of affected, we always have to take into account the Centimorgans. So for high risk, it's always 100 minus the Centimorgan. In our case, it would be 100 minus 2%, which equals to 98%. While low risk is always just Centimorgans, which in this case would be 2%. This is always important to write down, but especially write it down in fraction form. Now, what is 2%? In fractions, you can write it as like this, or you can divide it by 2 on both sides to get 1/50th. Up here, 98 might look a little bit more complicated. However, it's important to note that you can also just do the same as we did before, which is 98 over 100 divided by 2, which is equal to 49 over 50. Now to go into another example, so this is a little bit easier to understand. Here we have a 5% chance of 5 centimorgans for crossing over to occur. So here, with this person having a marker that marks for non-pathogenic alleles, there's still a 2 or 5% chance for this person for crossing over to occur, meaning there's a 5% chance for this person to be either affected or a carrier. Here, this person actually has the marker that marks for pathogenic allele, meaning that there is a chance that this healthy B has copied into this unhealthy A. Therefore, even though we can assume that there is 100% chance, we always have to take 100 minus the chance that the A is actually a B undercover, right? So minus 5% because we have 5 centimorgans. That is equal to 95%. So here we will have to write the high risk as 95%, while the low risk is 5%. And if we divide it into fractions, it would be 1 in 20 here, and then 19 in 20. Here it's there's a 10% chance of 10 centimorgans of crossing over to occur, and it's the same principle. Here there's a chance that this B is actually an A undercover because of the crossing over. So that's why we take, there's a 10% chance in our case here that crossing over has occurred and that this person is either affected or a carrier. While here, with a non-pathogenic crossing over, this would be our high chance that this person is affected because they are carrying the marker that marks for the pathogenic allele. But it wouldn't be 100% because they're still crossing over that could occur, which means that this B could have given its information to this A, meaning that there is a chance that this A is actually a B undercover. We take 100 minus the chance of crossing over to occur, which equals to 90%. So here our high risk would be 90%, which is 9 over 10, and our low risk would be 10%, which is 1 over 10. We can always remember it as high risk is 100 minus centimorgan, while low risk is centimorgan. Why? Because the high risk represents the fact that even though there's a high risk that this marker is correct, it could still be a B undercover. While here, even though there's a high risk that this marker is correct, it could still be an A undercover, meaning that there is a 10% chance of affected here, while here there's a 90% of being affected because the other 10 could mean that it's a B undercover. So the percentages are always representing the risk of being affected or a carrier, not the risk of being healthy. Number 3, prior probability is always parents' probability times high/low probability for carrier. So what we did up here with the centimorgans. Yes. Now, if we remember exactly from the previous colloquium, we use autosomal dominant and X-linked recessive pathologies. And in that case, we have to use Bayesian tables almost always. And that's why it's important to note that here, usually in the prior probability for the previous ones, we would take just the parent's probability times 1/2. So if a parent had, let's say, 2/3 of a probability to be a carrier, this child here would have half of it, which would be 1/3, etc. But in our case here, when Centimorgans comes into question, we already know if the child has gotten a pathogenic or non-pathogenic allele from the person, depending on the markers. However, the markers can be wrong depending on if crossing over has occurred or not. That's why we always have to take parent's chance times the high or low risk. So to be a carrier, it's often either high or low depending on what kind of marker you have. So to give this perspective, let's start with the pathogenic crossing over. So here we have a B marker, which stands for the non-pathogenic allele of the father. However, this B could still be an A undercover, depending on if this A has given the information to B during crossing over. And if there's a 2% chance of crossing over, this means there's a 2% chance for this person to be either affected or a carrier. However, let's say that we have a penetrance of 60%. And remember, if we have penetrance, we always have to use some sort of Bayesian table, as well as if we are unsure if this person is affected or carrier. Unsure means anything under 100%. So 2% is you being unsure. Therefore, with the prior probability, we take the parent's chance, which for us in our case would be 100 or 1, times the high/low risk. For us, it would be a low risk because of the healthy marker here. Healthy markers are usually right, but crossing over adds the additional risk, and it would be a low risk here. So we would have 2%, which also is represented by 150. And that is equal to 1 in 50. For non-carrier, the rest is always the same as we've always done. So for non-carrier probability, it's 1 minus 1/50th, which is equal to 49/50th. So we can write it down here. Conditional probability, I wrote penetrance at 60%, which would be 3/5. And then conditional probability for non-carrier is always 1. Joint probability are these two multiplied by one another, which would be 3/250, while non-carrier is 49/50, but since we want to simplify it, we have to write the denominators for the denominators to be the same. So in our case, 49 times 5, that would be 245 divided by 250. Now for the posterior probability, we'll just take the numerator for the left side on the top, divided by the numerator on the left side, plus the numerator on the right side, which would be 248. So the new and improved chance for this person to be a carrier would be 4 over, was it 4? It was 3, sorry. 3 over 248. Right here. Now we can do the same for non-pathogenic crossing over. So let's do that as well. So for the non-pathogenic, it means that this A could be a B undercover. However, the markers are usually right. That means that we have a high risk here. However, we still need to take into account that the crossing over could still occur. So even though we should assume that it's 100%, crossing over could still occur, meaning we have to take 100 minus the chance for crossing over, which would be 100 minus 2, and that is equal to 98%, or 49 over 50. So we can write that down here. The parent's chance is 1, because that's 100 over here, times the high/low risk. In our case, it's a high risk, so 49 over 50, which equals to 49 over 50 in and of itself. But sometimes the parent's chance will not be 1. Sometimes it can be something different. Here we just take 1 minus 49 over 50 in order to get 1 over 50. Then for the conditional probability, it's the penetrance here, so 3 over 5. And then here it would be 1. For the joint probability, it's these two multiplied by one another, which would be 147 divided by 250. And here it's 1/50th, but we will rewrite it into 5 over 250. Now for the posterior probability, we'll just take the numerator up top divided by the numerator on the left plus the numerator on the right, which would be 152, I believe. So the posterior probability is quite high. Why? Because we already know that it has this marker that marks for a pathogenic allele. So the probability will probably be very, very high. So here would be 147 divided by 152. All right, next up is the 5% chance. So I will just go through this very quickly because we just did this with the 2%, but just to give more examples. Again, it's always important to write high and low risk, and for 5%, 5% is also equal to 1 over 20. While the low risk is 95%, which is equal to 19 over 20. Let me just double check that. Yep. Why it's low and high risk like this, we can just go through it again. Here, there's a low risk for this person to be carrying this pathogenic allele because it doesn't match with the marker of the pathogenic allele. However, there's still a risk for crossing over to occur. So therefore, the risk for this person to be affected or a carrier is 5% for affected or carrier. While here, he is carrying the marker that marks for an affected allele. So in our case, there's still it would be 100. However, we have to take into account the crossing over could be occurring, which means this could still be a B undercover. So that's why we take 100 minus 5, which gives us 95%. This is the high risk, and this is the low risk. So here for prior probability, it's parent's chance times high or low risk. So let's take this one as an example. So the prior probability would be 1 times 95, which is 19 over 20, equal to 19 over 20. And for the non-conditional, it's just 1 minus the conditional prior probability, so 19 over 20. That is equal to 1 over 20. Did I say non-conditional? I meant non-carrier. For the conditional probability, it would be the penetrance, which I wrote down as 60%, so 3 over 5. These are all exactly the same as we do always. 19 times 3 would be 5t. 57 divided by 250 right here. Then here we would have 5 by 250. And then for posterior probability, we'll just take the numerator here. I hope I did that correctly. 57 divided by the numerator here plus the denominator, which is 62. This is a pretty high chance. Why? Because we do have a high chance for this person to be a carrier due to the fact that he is carrying this marker. However, again, it's not 100%. Why? Because this person can still have this marker while the allele that is marking for it could be a B undercover. Here I wanted to show you an example of when the parent's risk isn't 100%. And also an XR example. So we're not taking penetrance into account. Instead, we're doing the Bayesian tables for XR. So again, we always have to write the high risk versus the low risk. High risk is always 100 minus the CM, which would be 10. That is equal to 90% or 9 over 10. While the low risk is always just the CM. So 10% or 1 over 10. Now we come here. You have to remember for XR, what did I want to say? The chance for a person, we want to calculate the chance for a person to be affected. Now I wrote down that the pathological marker, or the marker that marks for pathological alleles, is D, so that it would be easier. But usually you have to cross-reference with the other affected individuals in the pedigree. In our case, D is the pathological marker. However, this person still has a 2 out of 3 chance of being a carrier, so let's ignore this D. And let's just say that this person has a 2 out of 3 of being a carrier, but we know that this is non-patho. So the C, or the marker that marks for C, is non-pathological. Okay. Then what does her daughter have in the case of XR? Usually in XR, we just took half of what the mother has, so 1/3 times, or not times, and then we took into account Bayesian in case she had one or several healthy sons without having an affected son. But in our case, we don't do that anymore. In our case here, we have to take, in prior probability, parent's chance times the high or low risk. So if the parent has 2/3, we have to write it down. First of all, let's one second. Yes, let's assume we have to first calculate. So here, of course, a child gets 1 from her dad and 1 from her mom. We say that she got the B from her dad and the C from her mom. So the chance, because we still don't know if this is pathological or not right here. So the chance for her to have the pathological is has to be the chance for crossing over to occur. So if this pathological had copied into this C right here, and that would be a 10% chance, right? 10%, which is a low chance because she has the non-pathological marker actually. While here, we don't know what she got from her mom, but we do know that she got a B from her dad. So she could have still gotten let's assume actually here that the mom is 100% affected, because otherwise it wouldn't work. So let's say that this daughter got an A from her mom, which is the pathological marker. However, this A could still be a C undercover, and therefore we take the high risk, which would be 90% for this A to be correctly marked. But let's start with the first one right here. So we have to take the parent's probability times the high or low risk, and for us we know it's 10%. So 2/3 times 1/10. because the mother here has 2/3 probability to be carrying a pathological allele, and the daughter here has 10% chance that her B or her C is actually the potential pathological allele in disguise. So here it would be equal to 2/30. Now for non-carrier, it would be 1 minus 2/30. That is equal to 28/30. The rest is just as we do always with XR. Remember, conditional probability for X-linked recessive is always the amount of healthy sons by the power of 2. So this person right here has 1 healthy son, so that would be 1/2. Sorry, it would be 1/2 by the power of amount of healthy sons. So she has 1 healthy son, which is 1, that is equal to 1/2. Here for non-carrier, it's always 1, and then we multiply these two by one another. We get 2/60, and here we get 28/60, over 30, and we want the denominators to be equalized here, so we can rewrite this as 56/60, and then we just take 2/58. Where did we get the 2? We got it here. Where did we get the 58? It was this plus this. And that would be our posterior probability for this mother, or not that mother, but this mother right here to be a carrier. So 2/58. Meanwhile here, if we know that the mother is carrying a marker that marks for the pathogenic allele, and the mother is 100% in that case, then there would be a high risk for this person to be a carrier or to be affected. But there would still be a lower than 100% risk due to the crossing over, because this A could just be a healthy C undercover. So that's why we take 100 minus 10 and we get 90%. And then for our, let's just rewrite it right here. For our Bayesian table, we would take parents' chance, which in our case is 100, times the high/low risk, which is in our case is high risk of 90 or 9/10. That is equal to 9/10. And then for non-carrier, it would be 1 minus 9/10, which is 1/10. Conditional probability is 1/2 by the power of amount of healthy sons, which would be 1/2 by the power of 1. That is equal to 1/2. Joint probability is prior times conditional, so that's 9/20. And here it's 1/10, but that can be rewritten into 2/20. And here we just take the numerator on top plus the numerator on the left side and the numerator on the right side, so 11. So the chance for this person to be affected carrier is pretty high, but it's still lower than 100% due to the fact that she has healthy sons and to the fact that there's crossing over occurring, and that would be 9/11. Alright, if we assume that crossing over has happened, then the marker showing the pathogen will change for the next generation. What does that mean? Let's assume that there has been a pathogenic crossing over occurring. That means that this B is actually an A undercover, so we assume that crossing over has occurred. This B is actually an A, right? Then, if we, for example, calculate this mother's or this father's probability to be, for this B to be an A, we say it's 5%. Then for the child right here, when we want to calculate the probability for this child to be sick, we have to take into account that they have gotten this B from the dad, that we are now making assumptions that is actually unhealthy and not healthy anymore. So as soon as we make an assumption that this is unhealthy, even though this is originally the unhealthy marker, we have to continue on with that assumption to further generations. So in our case here, we have to take in the chance that from father's side that it is a crossing over occurrence, and then we have to times it with the actual chance that this is another crossing over occurring, which would be 95%. How does that even work? Well, let's draw it up in simpler terms. So let's say we have this allele right here, and this is A. Then we have B right here. Now, this represents the father up right here. But the son right here, if crossing over has occurred, that means that the A has given up the information of the sick allele into the B. So we would have a B that looks something like this. Now this B, even though the marker isn't necessarily pathogenic of itself, it can be inherited down to the daughter. So if we assume that this B has this crossing over, this daughter now will have a very high chance that she will be pathogenic. In our case, there's a 5% chance of this occurring, but if the daughter has the B and the B marker, and the 5% thing is true, then the daughter will have an additional chance that this B actually is neutralized by this D now. So now instead of that B looking like that, we can have a B that looks like this. So we have to take into account that another crossing over has occurred here, which means that we have a pretty high chance that this B is actually just a normal B. So I know that sounds very complicated, but crossing over can occur in several generations, not just one. And if we assume that it has occurred on one generation, then that marker will be representing the pathogenic allele. However, another crossing over could have also occurred. So we take the 5% chance that crossing over has occurred from the dad. Now, if the daughter has the B, and we assume that the pathogenic allele is now undercover as the B marker, we also have to take into account that there is a high chance for this to be the pathogenic marker, but not 100%, because there still could be crossing over occurring, meaning if it's high, we always take this minus this, which is 95%. So here it would be 5 times 95% chance for this person to have a pathogenic allele. I know this sounds a little bit complicated, but hopefully it will make more sense when I go through the answers, right? Let me just put on a charger right now. There we go. Next rule, if the child doesn't have any telling markers, or we don't know which marker the child has gotten from a parent, there's an unknown risk of crossing over, meaning we revert back to the half of parent probability, like we did with all of the previous calculations for colloquium 1. Let's say we have this child right here, and we know that the parent has the marker that marks for pathogenic alleles, which is A, but the only thing we know from the kid is that he got the D from the mother. We don't know what he got from the father. So in here, we say that this is autosomal dominant because of our Punnett square. If we write it up, A. There's a 2 out of 4 chance, or 1.5, that this child will receive the dominant allele or the pathogenic allele, even though we don't have any markers. We just revert back to our old days. Same thing here, it would be 1/2. And then here, we actually don't know what kind of marks for the unhealthy allele. So this is a very important case that we have to remember. Which of these A's represents the unhealthy allele? We don't really know, but we know that this kid has gotten one of the A's, of course. We just don't know which one is healthy or unhealthy. So that therefore we also revert back to the half idea right here. Finally, if there's no penetrance or 100% penetrance, no penetrance means that there's no penetrance mentioned in the question, or the penetrance is mentioned and it's 100%, then there is no Bayesian table needed. Why? Because Bayesian tables are always used when we're not sure about if a person is a carrier or not due to penetrance or due to healthy sons. Well, here, there's actually a 100% chance that the penetrance will be affecting the person, or the unhealthy allele will be affecting the person. Therefore, there's no Bayesian table needed. Therefore, in our case here, let's say this person has an A. There's a high risk that this person is affected. Still a crossing over risk. Let's say that the Centimorgans is 2 cm. Therefore, there's a 2%, there's a 98% chance for this person to be affected, because there's 2% chance that this A is actually this healthy B undercover. We don't need to do any Bayesian table here. Okay, finally we can start with the calculations. Let me just bring up my phone. Sorry, it's taking a while to download my notes. Here we go. All right, the first question. X recessive disease, so we know it's XR, and the subsequent rules that follow the XR pathologies. The marker is located 5 centimorgans from the mutation. What is the probability that 2,2 is a carrier? So let's start with immediately writing down the high versus the low risk. Now, high risk is always 1 minus the centimorgans, or let's do 100 minus centimorgans, which would be 95%, right? Because 100 minus 5 is 95. Low risk is just centimorgans, which is 5%. Now we want to know if 2,2 is a carrier, so it's this person. In this case, we can see that the markers have been marked. Sorry, we're using numbers as for markers instead of letters here. So let's start with also writing down the common marker for affected, the one that they share between themselves. And in our case, they have an 8 each. That means that the 8 is probably the marker for affected individuals. So that immediately you have to write down because it makes everything a lot more easier. Now remember, XR means that the daughter can still be a carrier, but even though they're a carrier, they don't have to necessarily exhibit any symptoms, because the daughter has 2 X's, so even though 1 X is affected, it's enough to have the one healthy X for this affected X to not be important. Well, for guys, they only have 1 X, so if they have an affected X, that means that they will be affected because they can't rely on an additional X to help them out. Now this mother right here, who has given birth to both this son and this son right here, has this allele that she has given to each son, which has made them affected, which is marked by the number 8. This daughter right here, of whom we want to know if she's a carrier or not, doesn't have this 8 marker. She has 7, which she gets from her mom, and 12, which she gets from her dad. So her risk of being a carrier is very low because the marker doesn't match up with the common affected marker, which is 8. So in our case, the low risk we know is just this, the CM, because there's still a risk that this 7 is actually an 8 undercover due to crossing over. So in our case, it would just be 5%, just like this. So the answer to this question is simply 5%, or if we want to write it in fractions, 1 in 20. Okay. Next up is this person right here, and we're dealing with Huntington disease, which is autosomal dominant. But we don't have any penetrance, and if we look at the rules right here, no penetrance means no Bayesian table needed. So we just go according to the crossing over risk. Now we have to write down the high versus low risk immediately. We have 2 right here, so high risk is equal to 100 minus 2, which is 98%. In fractions, that would be 49 in 50. While low risk would be just the 2% or the 1 in 50. If we look at here, we have to also know the common marker for affected. We can see here that the common marker is probably A, because even though this person has both an A and a B, this person has 2 A's, so one of those A's has to be the the marker for the sick allele. So the common marker would be A. We're asking what is the chance for 3 or 2, 3 to be, we ask actually for 3 people. We're asking for 2, 1, which is this person right here, 2, 3, which is this person right here, and 2, 4, this person here, to become sick. So let's go with 2, 1. This person has the A marker, as well as the B marker. However, we can see here that this mother right here also has the A marker. Just because a marker is used or a same marker is used doesn't mean that it represents the same allele. So it can be the same marker. This marker can represent a healthy allele because obviously the mother is healthy. And then this marker can represent the unhealthy allele because the father is unhealthy. But which did we get it from? Did we get it from the dad or did we get it from the mom? This we actually don't know. And again, if we are unsure of something, if the child doesn't have any telling markers or we don't know which marker child has gotten from parent, there's an unknown risk of crossing over, meaning we revert back to 1/2 of parent probability. So in our case here, we don't know where from whom this A has come from. Therefore, we just revert back to the 50% idea or 1/2 idea. Why? Because let's say that this represents the father and this represents the mother here. You can see here there's a 50% chance that we receive the unhealthy allele from the dad. Therefore, this would be 50%. Now for 2, 3 to be sick, we can see here that the 2, 3 has actually 2 markers that are healthy. One from the mom Let's delete some things here. One from the mom right here and one from the dad. However, this allele right here could still be an A undercover. There's still a chance for crossing over to occur and for this person to be a carrier, but it's a low chance. Why? Because the chance of this person being affected relies heavily on the fact that the crossing over has occurred. And the low risk for us is 1 in 50 right here. Or a 2% chance, if you will, if you go according to just the CM chance. Now for the AC right here, oh, I remember this. So this is a very funny type of question. Where did this C come from, huh? You can assume immediately, actually, some very bright students in our class assumed that this was some sort of de novo mutation, meaning that maybe this B right here turns into a C, right? So some sort of de novo mutation occurred here, which is a very, very smart thing to think of, but most probably in real life examples, we're dealing with some sort of just got a message. Some sort of affair. So there's probably a dad here who has a C, and there's a link between this mom and this dad going in, creating this child right here. So that's probably what is occurring here according to our professors, although the idea of this being a de novo mutation generally true when it comes in the context of calculations and what is written on paper. You should always assume that the pedigree tree is 100% right. But when it comes to real life occurrence, usually a sudden different allele from what the parents has usually means there's been some sort of unfaithfulness happening, and there's probably another dad in the mix. Why dad? Why not? Why is the mom unfaithful, not the dad? Well, because you kind of know if the mom has been unfaithful depending on if she's pregnant or not. Well, the dad can't just pop up with a new child from a separate marriage without the mom knowing, right? So usually here, this is what is happening. However, let's just assume this is de novo, or let's just assume this is from another dad. Then we know that this child has gotten this A this A from his mom, because this has come from a separate dad, and this A we know for sure has come from his mom. So here we can say for certain that there's 0% chance of this person to be affected due to the fact that this father right here is not his biological father. So in the answer sheet, you will see a 0% here. However, let's assume that this is actually de novo mutation. So let's say that we know for sure that this is a de novo mutation of this allele right here. Then we would know for sure that this person right here has gotten that allele from his dad. So in this case, we would have a very high chance for this person to be a carrier or affected. And the high risk is 98%, or 49/50. So that is in case we know that for sure, because again, even if it was de novo, we couldn't say for sure that this de novo mutation didn't come from the dad or the mom. We don't really know for sure. But if we assume that the de novo came from the mom, then we know that the A came from the dad. Okay, next question. I think that was all. Yeah. Next question, autosomal dominant disease, so AD. We don't have any penetrance, we don't do any Bayesian tables here. Manifested after 40 years, 3-1 is 20 years old and wants to know what is his probability of being affected. So 3-1 is this person right here. Now for the markers, or let's start with doing high versus, actually we don't have any, we don't have any, what is it called? Centimorgans mentioned here. So there's no CM mentioned, meaning that we're not using any markers here. So if there's no markers, we revert back to what we know, which is the 1/2 idea. Or the fact that there is no crossing over happening. So we know for sure that there's no crossing over happening if there's no centimorgans mentioned in the actual question. So in our case, we have AB here. What is our common marker between all the affected for affected? Here we can see that all these affected have AB. So we're not really that sure which of these, because it's an autosomal dominant, so it only has to be one of these is actually the one for unaffected. However, we can also go to the unaffected side of the family, and they don't have any B in as a marker. So then we can assume that the B here is actually the one that makes all of these individuals ill. So it would be the B mark. Again, the mark doesn't make you ill, but the mark marks for a pathogen which makes you ill. And because there is no centimorgan mentioned, meaning there's no crossing over, if you have this B, 100% of the time you will be affected. So here this person unfortunately has this B, so he will be 100% affected, or a carrier at least. And that is it for question 3. We go to question 4. Huntington disease, which is again AD. There's no penetrance mentioned, so no Bayesian table needed. And the mutation is located 2cm. So we start with the high versus low risk. So high risk, low risk, and then the common patho marker. So the high risk for us would be 100% minus CM, which is 2. That is 98%, or 49/50. While the low risk is just the CM, which is 2%, or 1/50. And the common patho marker, we can see here, all of the healthy individuals have homozygous markers, while the non-healthy have this B marker, so we can immediately assume it's B. And now we're interested if this person has a chance to be sick, also this person right here. So both 3-1 and 3-2. So for 3-1, he has a high chance. Why? Because he has this B marker that marks for the pathogenic allele. So therefore he will have the high risk, which is 49/50. Why not 100? Because crossing over could occur, and this B could actually be just an A undercover. While 3-2 has 2 A's, just like some healthy parents. However, this A could still be a B undercover depending on if crossing over occurs. So there's a low risk for crossing over to occur. There's a low risk for this person to be affected. Low risk is 1 in 50. Just like that, because this A could still be the pathogenic B right here due to crossing over. Next up is X recessive disease, so XR. And 2-4 is pregnant and is going to deliver a boy. What is the probability that the boy will be affected? Marker is located God, why do I always forget what it's called? 2 centimorgans away from the disease-causing mutation. Okay, So first of all, let's do high versus low risk. The high risk is 100 minus 2, which is equal to 98%, or 49 over 50. While the low risk is equal to 2%, or just the CM, that is equal to 2%, or 1 over 50. So these two. And now for the common pathomarker. Pathomarker. And that's going to be B right here. We don't know the markers for these, but we do know for this. And that would be B. Okay, and now we want to know what is the probability for 2,4 to be a carrier of the disease-causing mutation. And what is the chance for her son, we know it's a son, to be affected. All right, so first of all, we can immediately assume that this person is not carrying, sorry, let me just look at my notes to be sure that I'm doing something right. Is not carrying the B that she gets from her mom. Why is that important? Well, isn't she carrying the B? Shouldn't it be a high risk because the common pathomarker is a B, so we would have a high risk here? Not actually, because you can see here, when it comes to X-linked recessive pathology, the mother is a carrier while the father is not. So the mother can make her son affected. So in our case here, what she got from her mom is actually A, which is the carrier here, because the dad, if he was a carrier, he would have been affected. Remember, XR. So she got the A from her mom, and we know that for sure because the dad doesn't have an A. And the B she got for sure from her dad, which means this is the non-patho B. Just because the common pathological marker is a B doesn't mean that all B's are the pathological markers. Because this B is a variant of a non-pathological marker. Why? Because we know for sure that this dad is not a carrier since he's not affected. Because guys who are affected always are carriers, always. And he gives this B to his daughter, so the daughter must have gotten her A from her mom and not the B. So this B right here is the patho B. Why? Because her sons are affected, so her sons must have gotten this pathological B. Just like this guy right here, and just like this daughter right here, because why? This daughter got 1 B from her dad and 1 B from her mom, and this is the patho B. We know for sure that she's carrying the patho B, which she must have given to her son as well. But here, for this girl right here, she's gotten 1 B from her dad and an A from her mom, because the only one who could have given her an A is the mom right here. So she has a pretty low chance of being a carrier. Here, however, we don't have a penetrance, but since it's X-linked R, we have to assume Bayesian table. Why? Because even though this mother has a low risk, she has 3 healthy sons. So we need to do a Bayesian table for her here. And in this case, I'm just going to copy template for a Bayesian table I did right here. So it's easier for me to go through this. Just like that. Perfect. So her prior probability is going to be the probability for her parent to be a carrier, which is 100%. Why? Because she has unhealthy sons. So 1 times the probability of either a high or low risk. For her, it's a low risk because she's not carrying the marker that marks for pathological allele, because she's carrying the A from her mom. The B must have come from her mom in order for her to be a high-risk carrier, but in this case, the only thing she got from her mom is the A, because she could have only gotten the A from her mom. So it'd be a low risk, which is 1 out of 50. That would be 1 out of 50. While non-conditional, it's just 1 minus 1 out of 50, which is 49 over 50. Here would be 1. For the conditional probability, we take 1/2 by the power of healthy sons. And this girl right here has 1, 2, 3 healthy sons. So 3, that is equal to 1 over 8. And now for my trusty calculator, this would be 1 over 400 because it's just these two multiplied by one another. And here it would be 49 over 50, but because we want the denominators to be equalized, we can write it as 392 over 400. And here we take the numerator up top times the numerator on the left side plus the numerators, not times, divided by the numerator on the left side plus the numerator on the right side, which would be 393. So the chance for this mother to be a carrier in our case would be 1 over 393. And now we calculate for the child's probability to be affected. And remember, we can write a Punnett square here, not a Bayesian table, sorry. And we assume that the mother is a carrier in our case. The father is not a carrier. Why? Because the father is unaffected. So here we do something like this. And we know that for sure this unborn child is a man because it's been written for us. So we can get rid of the female carrier type or options, and we get the chance that there's 1 out of 2 chance for this child to be affected right here. So we have to take parents' chance to be a carrier, which is 1 over 393 times child's chance to be affected, which is in our case 1 over 2. And that is equal to 1 over 786. Okay, next up right here, retinoblastoma with a penetrance of 80%. And because we have a penetrance, we know that it's AD, and we know that we have to probably use a Bayesian table here. What is the probability that the baby will be affected if we know that the marker is located 5 centimeters? God, 5 centimorgans from the mutation. Okay. First of all, let's write down the high and low risk. So high would be 100 minus the centimorgans, which is equal to 95%, or 19 over 20. While the low risk is equal to 5, which is 5%, or 1 over 20. And now we do the common marker, common pathomarker. And in our case here, that would be, I believe, A, because this person has 2 A's and they're still affected. This person has an A and a B and they are affected. So I believe that we're dealing with A as the common pathomarker. Okay. And now we can actually start. So here we know this person is 100% a carrier, and this person as well as this person. We are interested in what this child right here, the chance for this child to be affected, right? So let's start with knowing what the parents have. So here we know for sure that this parent is a non-carrier. He has 0% chance here. So we're actually just looking at the mom here. So this we're not interested in, we're just looking at the mom. So the mom in our case has gotten something, either this A or this A from her dad. And we don't really know which one. Now remember, let's see here. If the child doesn't have any telling markers, or we don't know which marker the child has gotten from parent, there's an unknown risk of crossing over, meaning we revert back to 1/2 of parent probability. So in this case, we don't know if, we know for sure that this B must have come from the mom, because the only way she could have gotten a B is from her mom. But so this A has to be either the non-pathogenic or the pathogenic A from her dad. Therefore, we have to draw a Punnett square, because again, we're unsure about her chance of being a carrier, and we do have penetrance, not a Punnett square, Bayesian table, sorry. And instead of doing the prior probability as parents' probability times high or low risk, in this case we're reverting it back to parents' probability, which in our case is 1 right here, times 1/2, which is equal to 1/2. So we're reverting back to our old system because we're unsure which, if she has gotten the A from her dad that is sick, or the A from her that is healthy from her dad. So here would be 1/2, here would be 1/2 as well, and then the penetrance is 80%, so the healthy chance would be 1 in 5. Let me just write it correctly. Here would be 1, here would be 1/10, 1/2, which is equal to 5/10 to equalize the numerators. This would be 1/6. So the mom's probability here to be a carrier is actually 1/6. And now for the child right here. We know the child's probability, or we know the child's marker immediately. So we know for sure that this child has gotten a B from her mom and a B from the dad. So will this child's chance to be a carrier be 0% or affected even 0%? Well, not really. Here we will assume that we go according to the fact that the mom is actually a carrier, which is 1/6. Now we do multiplications. What is the chance for one of these alleles to be sick despite actually marking for healthy alleles? Well, that's if one of them is actually undercover because they have been mutated during crossing over, pretty much. So this A, if it's sick, has given this B a mutation. So this B continues on, looking healthy, but it's actually an A undercover, right? So for us in our case, it's a low risk for crossing over to occur because again, it's a healthy marker and there's a low risk for crossing over. So low would be 5% or 1 in 20. And then, even though this child would have an unhealthy allele, even though this would have been an A undercover, right, due to crossing over, this child still needs to be part of the 80% that are actually sick. So we have to write in the penetrance. And this is equal to 4/600, or we can divide it by 4 on each side and get 1/150 as our answer here. We're done with the first part. Yay, the easy part. Now we have to go to the second part. And this part is very much more difficult than the first part. However, our professor did say that one of the questions in the colloquiums will look like this or one of the calculations from this document. But bear with me because this is a very, very complicated, or some very, very complicated calculations. I think there's only 5 of them, however, so hopefully we'll get through them easily, all right? Start with the first one. We have an autosomal dominant pathology, so it's AD, with a penetrance of 60%. Now the distance between marker is 5 centimorgans. Damn. All right, 5 centimorgans. So now we can immediately write down our high risk, which would be 100 minus 5, and that is equal to 95%, or 19 over 20. And then our low risk is 5, or that's 5%, which is equal to 1 over 20. And just get rid of the writing aid right now. And now we can also look for our common pathomarker. So in our case, it would be an A, right? Because the common markers between these affected people is A. Now, the first question. What is the chance for 2-3 to be heterozygote? Remember, heterozygote, not affected. So 2-3, 1-2, 1-2-3, that's this person right here. What is the chance for them to be a carrier? Now here we can see, let me actually bring it up so I'm saying the right things and not the wrong things. So here we can see that the C this person has gotten must have come from the mother, and the A must have come from the father. But just like previously with this person right here, we don't know which of the A's this person has gotten. It's unknown if this person got the healthy or the unhealthy allele that marks for A. So in our case, we revert back to what we know, which would be half. However, since this is autosomal dominant and we are unsure of this person's probability, we have to use what? A Bayesian table. So here, for prior probability, we would have 1/2. Right here, we would have 1/2. Conditional probability is 1 minus the penetrance, which would be 40%, or 2/5. Here would be 1. Then here we would be 2 over 10. And here it would be 1/2, which can be rewritten into 5 over 10. Then here we take the top, which would be 2, divided by 2 plus 5, which is 7. So the chance for this person to be a carrier is actually 2 over 7, due to the fact that we don't know which of the alleles that he got from the father. So we revert back to the old system. So here it's 2 over 7. Let's use another color for the next person. Let's color this red so it's easier to follow. Okay. Sorry. So the next person is 3-4, and we're asking what is the chance for this person to be heterozygote. So 3-4 would be this person right here. And very unique thing about this person is that they have no markers. So no markers. So we don't know what they got either from mom or dad. And therefore, if we're unsure if there's no markers or we're not sure which marker they got, we have to revert back to our old system, which is 1/2 of what the parent has. So in this case, right here. 1/2 of what the parent has is 1/7, but we can write it down so it's easier to follow. 1/7. I don't know why my iPad is being all wiggly today. 1/7. And the non-carrier is just 1 minus 1/7, which is equal to 8/7. Conditional probability is the same as before, that's 2/5. And meanwhile here it's always 1. And then we just take joint probability, which in this case would be 2/35 here. And then 8/7 can be rewritten into 30/35, I believe. Sometimes, guys, my brain isn't working as it should. So this is 6/7 and not 8/7. That makes no sense. All right, 30/35 here and 2/35 here. And then we take the top here, divided by the top plus the bottom, which would be 32. Not the top plus the bottom, the top here as well as the top here to get 32. So now we know that the chance for this person to be a carrier is 2/32 or 1/16 if we simplify it like this. So the answer here is 1/16. Now we can use the green marker for 4/1. 4/1 is right here. And they ask, what is the chance for 4/1 to be affected? So in our case here, remember, we know that the common pathomarker is A. So if we look at the nearest affected person, it's this person right here. Now he has given his daughter, which is the one that would be carrying this allelic variant, he has actually given her a C, not an A. But again, due to the fact that there could be crossing over occurring, we can still actually use the green color here and not use red. He has given her a C, but there still could be a crossing over occurring. However, the chance for her to be a carrier due to crossing over is very low. And what is the low chance? It's actually 5% or 1 in 20. But we still need to do a Bayesian table for her because we're unsure of her being a carrier, as well as the fact that we're not sure if she has this crossing over occurring or not. And in that case, we have to take parent's risk, which is 100, as we can see here, for the prior probability. Carrier, non-carrier. Why did I do that again? Why not just use the one that I've specifically made for this? Color green. So it would be 1 times the low or high risk, which in our case is 5% or 1/20. So 1 times 1/20 equals to 1/20. For the non-carrier, it's just 1 minus 1/20. That is 19/20. For the conditional probability, we will have the same as always, which is 1 minus 60%. That is 2/5 or 40%. And here it's always 1. Joint probability is 2 over... why am I having a hard time here? 2/100. Oh, sorry. And here it would be 19/20, which is also equal to 95/100. I think, let me just double check this with my calculator so I'm not making a mistake. 19 times 5, yeah, 95 over 100. Now we take the top here, divided by top here on the left, plus top on the right, so 97. So the chance for this mother to actually have the C to be an undercover affected, as well as the chance for her to skip the penetrance, would be 2 in 97. And now we can calculate for this child's chance to be affected. So in order for this child to be affected, let's draw a Punnett square. That's a great Punnett square. I don't know why my iPad is doing this. Wow. There we go. And we assume that the mother is a carrier, but we assume that the father is not. So the child, in order for the child to be affected, he needs to be getting one of these unhealthy alleles, which is 1 in 2, times the chance for this mother to actually be this phenotype, which is 2 out of 97. And then even if this child gets this phenotype, there's still a chance that he skips the penetrance. So we have to write in the penetrance there. So that would be, let's actually write it in here, 3 over 5. And that is equal to 6 over 970, which we can simplify to 3 over 485. We don't have any markers here. We don't know what the child is, so we revert back to our old idea of calculating. So here for 4-1 would be 3 out of 485. Now for D is a little bit different. D asks for the same child, the chance for him to be affected if he instead had 2 markers, which would be CC. Now remember what I said about if we assume crossing over occurs, then the marker for the common pathological allele would be changed as well. Let's look at the rule book again. If we assume crossing over has happened, then the marker showing the pathogen will change for the next generation. So in our case here, we are assuming that this mother has had this crossing over occurring. Then if this child gets this C from the mother, we will also assume that this is actually the pathological marker that he has gotten. So in our case, instead of reverting to the 1/2 rule, we actually have to rewrite this. Let's actually use another pen for it. So let's use light green. So in our case, we will still have to take the mother's chance to actually have this pathological C times the chance, not the chance for the child to be receiving the pathological allele, because we already know that the child has been receiving, has received it. Instead, we take it times the high risk of this child not having crossing over occurring, right? Because even if he gets this C from his mom right here, there's still a chance that this C is actually an undercover F due to the crossing over. So high risk for being affected is 19 over 20, which means we write in 19 over 20. And then we multiply it, of course, by the penetrance, because there's still a chance that this kid escapes the penetrance. And this will be equal to a number that I haven't written down, but I will calculate it for you guys right now. 97 times 20 times 5 equals to 9,700 divided by, or then 2 times 19 times 3 is 114. Pretty sure you can simplify it with 2 here. You get 57 over, so what is that? 4850. So here you would get 57 over 4850. Okay, next one. What is the chance for 4-3 to be heterozygote? 4-3, 1, 2, 3, 4. And it's this person right here. And now we can look to the closest relative that is affected, which is this person right here. He has an A, which is a common pathogenic marker, and he must have gotten it from his mom, because the only one that he could have gotten it is his mom, of course. Now the mom could have given it to this son right here. However, there's still a low risk for this child to have gone a crossing over thing occurring, because again, the only chance for this child to get this pathogenic marker would have been if he got it from his mom. But this A could still be a C undercover, right? So we need to draw a Bayesian table here. This time I actually remembered that I have the template. Whoop. But I don't remember which tool to use, I guess. Color, orange, and now for the prior probability, it's always going to be the high or low chance. In this case, this child has a high chance of being being a carrier due to the fact that this matches with the pathogenic common allele here. However, there's still a chance for crossing over for this to be a C undercover. So there's a high chance that there's 19 over 20. So mother's chance, which is 1 over 19 times 19 over 20, which is 19 over 20. Why is the mother's chance 1? That's because she has an unhealthy son. The non-carrier would just be 1 minus 19 over 20, and that is equal to 1 over 20. Conditional probability is same as always, which is 40% or 2 over 5. Here it's 1. And then, let me use, the joint is 38 over 100 here. And then on this side, it's 1 in 20, but we can rewrite it as 5 over 100. And then for posterior probability, we have the top here divided by left plus right side, so 43. So the chance for this person to be a carrier is 38 over 43, just like the Bayesian table says. Now we assume that this is the pathogenic allele. Now for him to have given something pathogenic to his daughter, it would be a very low chance. Why? Because the B, first of all, must have been given from her mom, but the only thing that the dad could have given her then is the C. And the only way for her to be a carrier then is if the C is actually an A undercover due to crossing over. But that would only be a low chance, right? So we assume low chance again, which is 5%. And then we do a Bayesian table for her as well. So let me just move this to the side a little bit, like that. And then paste this one, let's make it pink. Now, low chance for us was 1 in 20 right here. So we take 1 in 20 times the chance for her parents, or for her parent to be affected, which is 38 over 43, or not affected, but a carrier, of course. And this is equal to 19 over 430. Now I only simplified it, but you can calculate it normally as well. And then for non-carrier, it would of course be 1 minus 19 over 430, which in our case would be 411 divided by 430. Conditional probability is the same as always, 40%, which is 2 over 5. And here would be 1, and then the joint probability is these multiplied by one another, which would be 38 over 2150. And here it would be 411 over 430, but we can multiply it to get the denominators to be equal. That would give us 2055 over 2150. What did I just do here? Here we had to take 5 and multiply it by 430 to get 2150. So I did the same thing. I took 5 and multiplied it by the numerator and the denominator. And I got these two right here. Now for the posterior, we'll just take 38 on the top, divided by 38 plus 2055, which would be 2093. And that would be the risk of her to be a carrier. So here we would write 38 over 2093. And that is it for this calculation. So if you want to take a screenshot or you want to take a little pause, you can do that right now. Next up is number 2. Here we are dealing with autosomal dominant again, so AD. And we have a CM of 2%, so let's write the high versus low probability again. 100 minus 2, which equals 98, or 49 over 50. And the low would be just 2, and that is equal to 2, or 1 over 50. And then we also can look at the common pathomarker, which in our case would be E, because the ones that these two share is actually E. So we write down E. And now we can start with the actual calculations. 3, 2, what is the chance for them to be heterozygote? So 3, 2, 1, 2, 3, 1, 2. This is 3, 2. Now 3, 2 has gotten 1 E from the mom and 1 E from the dad. And we know that the E is the common pathomarker, so the chance for this person to be a carrier is actually quite high because the markers correlate with the pathogenic or non-pathogenic allele. However, there's still a chance that this E that the person got from the dad is actually a V undercover due to crossing over, right? Let me just delete these. So therefore, we have to do what? We have to do a Bayesian table right here, using the idea that there's a high risk, and the high risk is 49 over 50. So 49 over 50. So let's add the Bayesian table right here, like so. So the posterior probability is 40. Whoa, that's very thick. I guess that's just what we get right now. 49 over 50 times the parent's probability to be a carrier, which is 1 because he's affected. That is equal to 49 over 50. While non-conditional or non-carrier is 1 minus 49 over 50, which is equal to 1 over 50. Conditional probability is the rest of the penetrance, so it would be 80% in this case, 4 over 5. Well, here it would be 1. Now for the joint probability, let me see if I actually wrote it down somewhere, and I did. I'm a genius. 196 over 250. Well, here it would be 1 out of 50, which can be rewritten as 5 over 250. Posterior probability is just the top for the joint probability for the carrier type, and the top here plus the top here, which is equal to 210. And I believe that's it for this person. This person actually has a 196 over 210 chance to be a carrier, which is pretty high. So 196 over 210. Next one, what is the chance for 310 to be affected? So 310, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this person right here, ET guy. So ET has gotten what? He's gotten the T from the mom and the E from the dad. But we don't know which E it is. And remember, if the child doesn't have any telling markers, or we don't know which marker child has gone from parent, there's an unknown risk of crossing over, meaning we revert back to the 1/2 probability. So in our case here, we don't know if this E is pathogenic or non-pathogenic, so we will assume that normal probability. However, we don't know if this E is also an undercover E as well. So we have to do a Bayesian table for this dad too. Because yes, he's definitely gotten the pathogenic E from his mom, because he must have gotten the other one from his dad. However, this E could just be a C undercover due to the crossing over risk. Here we would have a high risk for this person to be affected overall, because the marker usually correlates to what kind of allele we have. However, let's do a Bayesian table for him anyway. It's right here like this. So let's color this in with blue. And because there's a high risk, we use 49 over 50 here. So 49 over 50 times the parent's risk to be a carrier. Because this person is affected, it has to be 1, which equals 49 over 50. Non-carrier is 1 minus 49 over 50, which would be 1 over 50. Conditional probability is the rest of the penetrance, which would be 80% or 4 over 5. And here would be 1. Now for the joint probability, we just take this times this. That would be 196 over 250. And for non-carrier, it's 150, which is also can be written to 5 over 250. Posterior probability is just this at the top. So 196 divided by this plus this. So 201. So the chance for this child or for this person to be a carrier, due to the fact that there is still a chance that this E is an undercover C due to crossing over, is 196 over 201. So now, because we don't know which E this person has gone from their dad, we take the dad's probability to be a carrier, which is 196 over 201, times the Punnett square probability. And the Punnett square probability for autosomal dominant is half of the whole, right? 2/4 is equal to 1/2. Because again, we don't know from which E this child has gotten, if it's the pathological or non-pathological E from the parent. So we go with what we know before, so 1/2. And now we multiply this by the penetrance, which is 20%. So that would be 1/5. And that is equal to 98/1005. This is just the simplified one answer. So here we write 98/1005. Next one, what is the chance for 4-1 to be affected? 4-1 is this kid right here. So now this will be a little bit more complicated. But let's start anyways. So this person right here, do we know if it has a common pathomarker? Well, we do know that this person is carrying an E, but is it the patho E? Well, we don't really know that, or actually we do, because this C right here must have come from the mom. So the only E this person could have gotten is the one from his dad. So that means that this person has a, let me just see here, has a 0% chance of being affected. However, this C right here could just be an E undercover, right? Due to crossing over. So this parent right here actually has a low chance of this being a E, or the pathological E, and the low chance we have is 1/50. And now we can do a Bayesian table. So let's start with this person right here. Color and green. So there's a 1/50 chance times the chance for the parent to be affected, and that is 1. And that is equal to 1/50. Then here we do 1 minus 1/50, and that is 49/50. Then conditional probability is same as always, 80%, so 4/5, and here it's 1. Then we have here 4/250, and here we have 49/50, or not simplifying it, but making the denominators equal, 245/250. And here we would take top here, divided by top here plus top here, so 249. So this parent's probability to be a carrier is actually 4/249. Now we go to this parent's probability, and because this parent must have gotten his E from his dad, why? Because the D definitely doesn't come from it. Actually, why am I looking at this person? I have to look at this person right here. So this person must have gotten the C from the dad. So for this person has gotten the C from the dad. So this person would and the dad has gotten the C from the mom, and the C is actually the one that could be potentially pathogenic. The C could be this E undercover, not this E. This E comes from the dad, so this E is irrelevant. So because the daughter could have only gotten the C from the dad, there's actually a high risk here that she would be affected. So 49/50. So that's why here we take 49/50 times the dad's chance to be affected, which is 4/249. And now it would actually be correct equal to 98 over 6,225. With non-carrier, you just take 1 minus 98 over 6,225, and you get 6,127 divided by 6,225. Conditional probability, same as always, 4 over 5, and here it's 4 over 5, and here would be 1. Joint probability is this the previous ones times one another, so it would be 392 over 31125. And here for non-conditional, we can simplify this into 30635 over 31125. Now I know it sounds like there's a lot of numbers here and it shouldn't be, but in some of these, and actually in colloquium, according to a professor, this could come up. And what did we do to get this? We actually just multiplied these by 5. So this times 5 and this times 5. And now we can put it up. So this would be on the top divided by this plus this, which would be 31027. And that is the chance that this person actually has 392 over 31027 to be affected. Now we can come finally to the child, and we know that the D must have come from the parents. So now it's actually the C that we think is pathogenic, not the D. But this D could be an undercover C. However, that's a low chance, and our low chance isn't 49 over 50, it's 1 over 50. So we would have 1 over 50 first, and then times the penetrance, which is 20%, times the mother's risk, which is 392 over 31,027. There we go. Again, I did the same mistake I did here. So I guess that we should write, we should just cross over the one that we don't think is pathogenic. So that one, as well as this one, we don't think is pathogenic. So that's how we can probably make sure that we're using the right numbers. If it's high or low risk, remember, this guy got the D from his mom. And this one is actually non-pathogenic because this comes from this mom, which is from the population. But this is the potentially pathogenic allele due to crossing over. Why did I do that? Oh, never mind. So this child didn't get the C. However, the D, due to crossing over, could have been a C or could be a C due to crossing over, which means there's a low risk for this D to be actually a pathological allele. Therefore, we take the low risk times the penetrance, because even if this is a pathological allele, there's still a chance that this child escapes the penetrance, times the chance for the parent to actually be affected. And this is equal to 392 over, this is going to be a long number, guys, 7,756,750, which we can simplify by dividing it by 2 and getting 196 over 3,878,375. That's what we would get here for this child chance to be affected. You can see it's pretty low. There we go. Now the chance for 4-2 to be affected. 4-2 is right over here. And then we can look at the parents right here. So the mother is insignificant, we're not interested in her. But the dad here has a brother that is affected, but we don't know his phenotype. However, look at this thing. There is a triangle shape going between these two brothers, and then there's a line between that angle, which almost looks like an A. It builds an A. This means that these children are monozygous twins, meaning that whatever this person has as a pathogen, as a as a, oh god, not pathogen, phenotype, this person has as well. So if this person is carrying, he just didn't miss the penetrance, he was actually part of the 20%, this person is a carrier as well. So we know for 100% certainty that this person is a carrier due to the fact that his monozygous twin is affected. Now, what is the chance for this child to be affected? We know that the only chance this child could have gotten the E is from the dad. We know that the E is the common pathogenic marker. So here, in this case, there's a high risk, of course, because the pathogenic allele, which is marked by E, has been given to the child. And there's a low risk that this E is actually a healthy R undercover. So therefore, we would have a high risk that this child is affected because the E does represent unhealthy alleles. So we would go according to the high risk chart. So that would be 49 over 250. And that is our answer here. 49 over 250. Let me just reiterate. This is the pathogenic marker. This pathogenic marker has gone down to the child. The child then will have a high risk of being affected or a carrier. However, due to the fact that crossing over could occur, which is a low risk, this E could be an R. In general, though, there is a high risk for this child to be a carrier. Therefore, we do 49 over 50. So that is it for number 2. Now we go down to number 3, which is X-linked recessive. And here actually I've come to be facing a problem with this type of calculation, specifically when we come to these individuals right here. But we will get to them later. Let's start with the first one, which is what is the chance for 3/8 to be a to be carrier of the pathogenic allele? Let's start with the high versus low risk. High risk is 100 minus the CM, which is 2. That is equal to 98 or 49 over 50. While the low risk would be just 2 or 2%. And that is equal to 1 over 50. Now the common allele or patho marker is D, as we can see here. So that would be D. Now, what is the chance for 3/8 to be a carrier of the pathogenic allele? 1, 2, 3, 1, 2, 3, 4, 4, 5, 6, 8, 7. Sorry, 1, 2, 3, 4, 5, 6, 7, 8. Oh my god, what am I doing with my calculations? 1, 2, 3, 4, 5, 6, 7, 8. So it's this person right here. Let me get rid of all of my... There we go. So that person right there, what is the chance for them to be a carrier? So we know here the D, this mother has to be a carrier 100% because she has given it to her son here. Now, what is the chance for this daughter to have gotten the D from her mom? So obviously, she must have gotten the D from her mom. However, what is the chance for crossing over to have occurred where this D is actually this healthy R undercover? So now we could have just added a percentage here for the low risk. However, due to the fact that this person has a healthy son, we also have to do a Bayesian table for her. Here, so her carrier probability, because it's a low risk, since she does have the marker from her mom, would be 1/50th. Sorry, it's a high risk because she does have a marker from her mom. It's a low risk of crossing over, high risk of her being affected or a carrier. So that would be 49/50 times the chance for her mom to be a carrier, which we know is 1. That is equal to 49/50. For non-carrier, we would have 1 minus 49/50, which is 1/50. Conditional probability is amount or 1/2 by the power of amount of healthy sons, and we only have one healthy son here, so it would be 1/2 by the power of 1, which equals to 1/2. Non-carrier would just be 1, and now we just take 140, there we go, and then here we can write it, like so. Here we can write it as 150, but to get equal numerators, we can write it as 2/100. Now here we just take 49, which is the top here, divided by 49 plus 2, which is equal to 51. That is the chance for her to be a carrier, if we take into account the possibility for crossing over to happen. Now we have to assume what is the chance for this daughter to be a carrier, and because we don't know, we can't see any markers, we have to just revert back to the Punnett square. And in our case, let's assume that our mother is a carrier, father is not. There we go. And we know for absolute certain that this person right here cannot be of the male carrier type, has to be the female. So there's 1 out of 2 chances for this person to be a carrier. So 1 out of 2, but then we have to multiply it by the amount, by the chance that this person, her mother is actually a carrier. So 1/2 multiplied by 49/51, that is equal to 49/102, pretty sure. Yeah, perfect. So this first would be 49/102. Next up, what is the chance for 1 to be affected? And that for 1 is right here. So for 1, we know that he got a Z from his mom. But again, crossing over could have happened. So let's start with knowing what is the chance for the mom to be a carrier. And her mom is 100% a carrier. Why? Because she has an affected child here. Now, this mom right here, the Z must have come from her dad, and the D must have come from the mom. And if the D comes from the mom, there's a high risk that this person is affected. So therefore, we assume the high risk value, which is 49/50. And because this person doesn't have any healthy sons, we just write down 49 over 50 as our normal probability for this person to be a carrier. Now this child right here has gotten this Z from their mom. That means that this person has a low chance to be affected. So we go according to the low chance right here, which is 1/50th. Why? Because this Z could still be a D undercover if there was some crossing over happening. So 1/50 times the child to be born affected, which in our case, if we look at the Punnett square, in order to be affected, you have to be born a male and you have to be born with the receiving the allele. However, we know that for certain, this person has not received the allele, right? So we ignore the Punnett square completely. We know that for certain this person has not received the allele. So instead, we just take the low probability times the probability for the mom to be to be a carrier, which is 49 over 50. And that is equal to 49 over 2,500. So here would be 49 over 2,500. There we go. Now for the green one, and the green one is going to be a little bit complicated because I don't understand the solution part, because I get another value than what is written in the solutions. So here we want to know what is the chance for 4-2 to be affected, and 4-2 is right here. Now in order for 4-2 to be affected, the mother has to be a carrier. And we know for sure that the common patho marker is D, which in our case we've already calculated the chance for this mother to be a carrier. This mother must have gotten the D from her mom, because there's no way she got the M for her mom because the mom doesn't have an M. So there's a high risk here. However, we have to do Bayesian table. Why? Because she has 2 healthy sons. Sorry, just need the Bayesian table template I have here. Here we go. Paste it right there. Superb. So she has a high risk of being a carrier because she has gotten the dominant or the recessive X from her mom. So high risk is 49 over 50. 49 over 50. Times the risk that her mother is actually a carrier, which is also 49 over 50. 49 over 50. And that is equal to, let me just see here, 2,401 over 2,500. Now, this is where the answer sheet tells us we are actually wrong. So if any of you has an idea of why this could be wrong, you can answer in the comments. Let's see here. 2C, as you can see here, it assumes, it's actually 3C. It assumes that the mother has a prior probability of 2,401 divided by 2,550. But if we look up here, 2,401 is true, but 2,550 I did not get. And I don't understand how this person got to that point. So I'm just assuming that I am correct, but I will ask my professor next week. However, do take this with a grain of salt, just because it's not what is written in the answer sheet. So 2,401, 1 minus 2,401 divided by 2,500, and that is equal to 99 over 2,500. Now, conditional probability is the amount of is 1/2 by the power of the amount of healthy sons, so 1/2 by the power of 2. That is equal to 1/4. Joint probability is the two previous ones multiplied by one another, so that would be 2,401 divided by 1,000. And here it would be 99 over 2,500, but that can be easily rewritten to 396 divided by 10,000. 1,000? 10,000, excuse me. So now we take the numerator for the top, 2,401, divided by this numerator plus this numerator. That is 2,797. And that is what we get for the chance for the mom to be a carrier. 2,797. Now, in order for the child to be a carrier, we don't really know what the child's markers are. So we will assume the Punnett square rule, and that is, in order for the child to be affected, it has to be born male and a carrier, so it's 1 out of 4. Therefore, we will have to write 1 out of 4 right there. And then we multiply it by the mother's chance to be a carrier, which is 2,401 divided by 2,401 divided by 2,797, which is equal to 2,401 divided by 11,188. That is the answer that I get for this part. However, again, this, according to the answer sheet, is wrong. It should be 2,550 here. And I don't know why. So if anybody has any ideas, please to listen to what you have to say. Next part is X-linked recessive lethal pathology. Now remember what we know about XR, and that's the Halden's law. If it's a lethal pathology, if it's XR of course first, and it's lethal, and it only affects one male, then the mother is 2/3 chance a heterozygous carrier. So in our case, we only have one affected male, and it is, as the question suggests, lethal. Therefore, we assume that the mother is 2/3 affected. Or not affected, but a carrier. There's no crossing over occurring here because this is just a universal rule. But now we'll write down the high and low risk. So we have a high risk of 100 minus the CM, which is 8, which would be 92%, or let's see here, 23 over 25. While the low risk is just the 8, or the 2 over 25. And then the common marker is A, because this person right here only has the A to show. Now we can go according to the normal rules. Right here, we know that this person has gotten the B from the dad and the A from the mom. So she has quite a high risk to be a carrier due to the fact that the A is the common pathological marker. However, we also have to take into account that this A could just be an S undercover due to crossing over occurring. So that's why we need to do a Bayesian table, not only because we're unsure, but because this person has 2 healthy sons, since it's XR. So here, there's a high chance, and our high chance is 23 divided by 25 times the mother's chance to be a carrier, which is 2 out of 3. That is equal to 46 out of 75. For non-carrier, it's 1 minus 46 out of 75, which is 29 over 75. Conditional probability is amount of healthy sun, or 1/2 by the power of amount of healthy sons. So 2, and that is equal to 1/4. Here would be 1. Joint probability together, 46 over 4 times 75 is 300. And here it's 29 over 75, but if we multiply both sides by 4, we will get 116 over 300. And here we take the numerator up here, divided by the numerator plus the numerator right there, which is 162. And we can divide these by 2 to get 23 out of 81. So the chance for this person to be a carrier is 23 over 81. Now we're asking what is the chance for 4-1 to be affected. So let's go down right here. This person hasn't gotten the, what do you call it? The common pathological marker from their mom, because the common pathological marker is A. So she will have a low risk. Why? Because this B could still be an A undercover if there is a crossing over occurring. 2 out of 25 times mother's risk of being a carrier, which is 23 out of 81. That is equal to 46 over 2025. So now we know the chance for this mother to be a carrier. So what is the chance for this child to be a carrier? We don't have any markers, or not a carrier, but an affected. Don't have any markers, and we can go according to the normal rules that we have for XR, which is that in order for this child to be sick, it has to be a carrier, and it has to be a man, so that's 1 out of 4. So 1 out of 4 times the mother's chance to be a carrier, which is 46 over 2025. And that equals to 46 out of 8,100, and we can divide it by 2 in order to get 23 over 4,050. That is the final answer for here. 4,050. There we go. We're finally on the last question, guys. Okay, last question. We have an autosomal dominant disease, and we have a penetrance of 70%, markers located 10 centimeters. Have I still not remembered how you call that? Yes. Centimorgans. 10 centimorgans away from the disease-causing allele. So let's immediately write high chance, which is 100 minus 10, that is equal to 90%, or 9 over 10, while the low chance is just 10, that is equal to 10%, or 1 over 10. And then the common pathoallele is, we have one person affected with a C and one other person affected with a C, so it would be a C. Now they ask, the first question is, what is the chance for 3-1 to be heterozygous? So 3-1 is 1, 2, 3. It's this person right here. For this person to be heterozygous, it needs to have gotten this C from this person right here. However, it has not. But despite this, we know for sure we actually don't. So we will just assume that this person could be affected. So this person could have gotten this C from the mother, which has contributed to this child being affected. So this mother is 100% a carrier. So this mother has a high risk of being a carrier as well, but we must assume that this C could also be a D undercover due to crossing over. So let's do a Bayesian table here. Color in red. So for the carrier prior probability, it's going to be mother's chance or the parent's chance to be a carrier, which is 100%, times the high or low probability. And because this parent has gone the pathogenic marker, there's a high chance. Therefore, it's 9 out of 10 here. So 9 out of 10, that is equal to 9 out of 10. For non-carrier, it's just 1 minus 9 out of 10, which is equal to 1 out of 10. Conditional probability is just the rest of penetrance. So if it's 70%, it's going to be 30%. Here it's 1. And down here for joint probability, that's 27 divided by 100. And here it would be 1 over 10, but that could also be written into 10 over 100. For posterior probability, it's just taking this at the top, divided by this plus this, so 37. And that is the chance for this person to be a carrier. Now, we're actually looking at this person right here, and has this person gotten the pathogenic allele marker from the mom? Yes, indeed they have, A right here. And the F must have come from the dad. So the A gives this a high chance for this person to be affected, right? Well, not really, because I fooled you there, or maybe I made a mistake. And the actual pathogenic risk, common pathogenic allele is C and not A. This person hasn't gotten the C from the mom, so therefore there's a low risk. Why? Because this A could still be a C undercover. So there's a low risk, and our low risk is 10%. So 1 in 10, and we add this into a Bayesian table. Like that. Let's make it actually pink to distinguish it. Like so. So the chance probability times the probability that the parent was a carrier, which is 27 divided by 37. And that is equal to 27 divided by 370. 1 minus 27 divided by 370 equals 343 by 370. 343 by 370. For conditional probability, that's the same as always. That's the rest of the penetrance, which is 30% or 3 out of 10. Here it's 1. Then finally joint is the subsequent ones, or the previous ones multiplied by one another, which would be 81 divided by 3700 here, and then 3430 by 3700, and that will give us 81 over, which is here, plus this, so 3511, which is the chance for this person to be a carrier. 81 by 3511. Finally, we get to 43. This will be the, this will be the final thing we do. Thank God. Okay, what is the chance for 43 today? Sorry. So we're not looking at this person right here. We're looking at this person here. Why? Because this person is... It's still weird. It's still very odd that you're doing a Bayesian table for... Is it really 3-5? Yeah. How come you do it for 3-5? Why do you do a Bayesian table on a population person? If anybody knows the question to that, please answer me. But I really don't know why you would do a Bayesian table on a person from population, because this person is from population, doesn't have anything to do with these people right here. So I assume that there was a mistake and this would have actually been on this side. Because again, I don't know how else you would have done a Bayesian table on a person from the population. That just doesn't make sense in my head. But I'm assuming it's an error. I'm assuming that this line right here would actually be going here, and this would not be there. So let's just assume that is true. 1/10 here. Oh God, let's first explain what we're doing. So this person got a D from their mom, which is not the pathogenic marker, so there would be a low chance. The low chance would be 1/10. And we multiply that. Why? Because here that's the low one. Multiply that by the mother's chance to be a carrier, which is 100, and that is 1/10. Non-carrier, it's just 1 minus 1/10. That is 9/10. Conditional probability is the same as always. It's the rest of the penetrance. So that's 3 over 10, or 30%. Here it's 1. Over here it would be 3 over 100. And over here would be 90 over 100 to equalize the denominators in order to make this step a lot easier. 93. So 93 we get from 3 plus 90, and 3 we just get from the top. So the chance for this mother here to be affected, if we assume that she's actually the daughter here, would be 3 over 93. Not affected, but a carrier, right? So we assume in that case that the D is the new pathogenic marker, is what we're assuming. So now for this son right here, we will also assume that there is a high risk. Why? Because this son has 2 Ds. The first he must have gotten from the dad, and the second he must have gotten from the mom. And since we are now assuming that the second, the D from the mom, is a pathogenic marker, because we're assuming that there is cross oh God, cross-reference, I almost said. What is it called? Jesus, I'm just having the biggest brain fart right now. Crossing over. There's crossing over occurring here that we're assuming is happening. Due to the fact that we're assuming that this is the probability for the person to be a carrier, that means that this would be a high chance, since this is now the pathogenic marker. The high chance is 9 over 10. 9 over 10. But we have to do another Bayesian table for this person. So let's draw that. And it would be, it would be probably the final Bayesian table I ever do here. Or maybe not. Let's not jinx it. So we take the parent's chance to be a carrier, which is 3 over 93, times the high or low chance. In this case it's high, so 9 over 10. And that is equal to 27 over 930. So non-carrier would be 1 minus 27 over 930. And that is 903 over 930. For conditional probability, it's same as always. It's 30%. So 3 over 10. Here would be 1. Joint probability is the previous ones times one another. So 81 over 9,300 here. And here will be 90,030 divided by 9,300. Why? I just took this times 10, both of these. And now we can easily just take the numerator up top, divided by the numerator plus the numerator here, which would give us 9111. So the chance for this person to be a carrier is 81 divided by 9111. Now, what is the chance for this kid to be affected? And for this one, we actually know that the kid has gotten at least 1D from the dad. However, which one it is, if it's the pathogenic or not pathogenic, we actually don't know. And therefore, we revert back to our old days, which means we have to look at the Punnett square. And there is 1/2 out of the total chance for this child to have received the pathogenic marker out of these two. So it would be 1/2 times the chance for the father to be a carrier, which is 81 over 9111, times the chance for the child to be affected, which means he has to be part of the penetrance of 70%. So 7 over 10. And that is equal to 5103 divided by 911,100. And we can divide these by 3 in order to get 1701 divided by 303700. And that is the final calculation for this. 303. So sorry for the amount of faults and mistakes that I've done so far. Hopefully you've still been able to catch up. Only issue is, of course, this person right here doing a Bayesian table, as well as these people right here, because of this value right here, where the answer sheet says 2,550 instead of 2,500. Other than that, these should all be correct. I hope you guys enjoyed it. I'm going to send this document as well as the video on the chat. And I hope you guys have a wonderful evening or morning or day, whatever it is. And see you next time.